Okay, one that's called equilibrium problems now, although it does say here we've got acceleration, so these examples not all this example isn't fully in equilibrium. So got a box on a table, fairly simple contact to begin with, although helps with the no gap because it is in contact. So we've got 320g in terms of our mass, so we're better off calling that, hopefully should be comfortable, 0.32 kilograms. So I'll have a 0.32 g weight. Got a girl pushing down vertically on the block. So let me just change that to a different colour pen for my forces. Girl pushing down, sorry, weight first, 0.232 g. Girl pushing down, so call it P for pushing, I don't know, whatever you want. And that's a force of, it's a force of 8.2. Sorry. And the book is attached to a light inextensible string and a boy pulls the vertically upwards. So we've got a force coming upwards as well. Let's call it T for tension, they said here. And then we've just got one more force. So there's only one object and it's a reaction force going upwards to the book field from the table. We've only got one object, so we don't need the opposite and equal R. Okay? And it says here, express the normal reaction force in terms of T. So you could do this in the equilibrium for part A. So you could say forces up equal forces down because it is in part A in equilibrium effectively. So you could say that T plus R equals 8.2 plus 0.32 g. Or as we said before, you could pick a direction of kind of positive, and this one here, the book comes off the table, so you might think, right, well, I'll do it as up because maybe later there's some it is up, at which case you get T plus R minus 0.32 g minus 8.2 equals mass something times 0, so 0, but you will get the same equation. It's just, I think, when there is motion possible, acceleration possible, it can sometimes be better to think like this. Generally, with things lying on table, they don't always move up, but it will happen later anyway, so we will potentially need to be prepared for that. Going back to this, express the normal reaction. So we want R equals, and I'll add these in my calculator because it doesn't leave it in terms of G, and then we take away T, so something minus T. 8.2 plus 0.32 times 9.8, so it's 11.33. 11.34. I'm not going to leave it as 11.3, that's generally your 3 sig fig, but it should be okay. It's not just a final answer, it's got something else in it as well. I suppose that's newtons as well, might be important. Find the smallest value of T required to lift the book off the table. So what here is have a little bit of a spark of imagination. If the book comes off the table, what's going to change in terms of our forces? And the thing that's going to be important is that R will equal to 0 because there will be no contact anymore. And this is just a little spark you need to have in order to get this bit right in your mind. So R will be equal to 0, so we can say 11.34, so that we can probably see, well, T is going to equal to 11.34, or 11.3, I'm going to leave that as 3 sig fig properly now. Okay, so you might say R is equal to 0, you might say this is 0, but I don't think I need to necessarily show that. In fact, if I just leave that to 11.3, that makes more sense probably from part A to B. So that's a really important part. We only have that reaction force. It's a normal contact or normal reaction force, but it's a contact force. Okay? Only there if we actually are in contact with the surface. Right, what do we need to do for part C? So find the acceleration of the book when t equals 12. So here I did it as an F equals ma, so I'm just going to copy this. So if an F equals ma plus, then going upwards, so I'll have t as 12, so I'll have t. It is not in contact, so the reaction is not there. And this was the smallest value of t to which it would lift off, so anything, sorry, this one, anything bigger than that, again, it's not going to have contact, but if it's accelerating, clearly that's not going to be true anyway. Take away 0.32 g, take away 8.2, and it's equal to the mass, 0.32, times by A, which we don't know yet, that's what we're looking for. So I think I can just rearrange that straight away for A by putting all this in my calculator on the left-hand side and dividing by 0.32. So 12, take away 0.32 times 9.8, take away 8.2, decimal, divide by 0.32, and it gets me what's going around to 2.08 meters per second squared. And that's it. But again, it's just this idea about the reaction force disappearing. Effectively, it can be confusing about this example.